So now we have a number of spotlight talks where these are paper submissions that are going to talk for 3 minutes each. After the spotlight talks, we're going to have a coffee break so people can go and look at the papers that have just been talked about here.
So, hi everyone, I am Olivier Goudet, and I will present to you Causal Generative Neural Networks. So it's a joint work with Diviyan Kalainathan, Philippe, Caillou, Isabelle, Guyon, David Lopez-Paz, and Miche Sebag. So in this work we start with observational data, and we want to find the underlying causal structure from this data. So more precisely, we want to find a directed acyclic graph between all the variables. So one general way to represent this kind of causal mechanism is to use a functional causal model, saying that each variable is a function of its parents in the graph and of a random variable representing all the unobserved influences on each target variable. So here you can see an example of a functional causal model with 5 variables. And the idea is to model each causal mechanism with a generative neural network. And by doing this, we obtain kind of a big generative neural network, and we can simulate the joint distribution of the data by sampling all the noise variables and by passing them in one pass forward. So now we can sample data, and what we want is to find the directed acyclic graph, allowing to explain the best the observational data. So we explore the space of possible graphs, and each time we test a graph, we train it in order to minimize the maximum mean discrepancy. So this is a differentiable metric between the original data and the generated data. And we select the graph allowing to minimize this MMD score plus a penalization term depending on the total number of edges in the graph. So to summarize, our approach has many advantages. So because we can exploit both conditional independencies and distribution asymmetries of the data. And we can also model multiple interactions between the variables. The approach is also non-parametric in the sense that we do not make any assumptions on the form of the distributions, neither on the form of the causal mechanisms. And once learned, this model can be a simulation tool for practitioners in order to simulate interventions, for example. However, there is one main limitation, is that it's quite computationally expensive, but it is feasible for already for up to 50 variables. So we have, if we want to test it, we have a code available online, and so you can come and see our poster to have more details. Thank you very much.
Hello. Hi, I'm Sarah Tan, and I'm going to talk about detecting bias in black box models using transparent model distillation. This is joint work with Rich Caruana, Giles and Yin Lu. So, why are we here? Risk score models are really common in our lives. Examples of this include your credit score, insurance risk scores, hospital admissions risk scores, all kinds of risk scores like that. At the same time, they are frequently black box, and they are usually only available to people who create them and not the people who they actually affect. So in this paper, we take a look at the risk score as well as the actual outcome. This is a second target, And this, I want to highlight here that the actual outcome is actually what the risk score was supposed to predict. So a risk score could be your risk of default, which is 7 on the slides here, and the actual outcome is whether you actually default yes or no on the loan. We use a transparent model. We do model distillation to learn a transparent model that mimics this black box risk score. But we don't stop there. We go one step beyond that. So we learn the same class of transparent model to predict the actual outcome as well. Now we have 2 transparent models and we can compare them and detect any differences between them. And we are particularly interested if these kind of differences exist for protected variables like race or gender. Here is the approach demonstrated on the Compass recidivism risk score dataset. The red line is the mimic model of black box risk score, and the green line is the model of actual outcome. And the dashed lines are confidence intervals. These are important because when we detect differences, we want to know if they're really statistically significant or if they're just due to random noise. Here is a feature where the 2 models roughly agree. But here is another one, race, on the right, where there are certain race categories where the models don't agree. We also demonstrate the approach on 2 other datasets, Landing Club, and which is a loan dataset, and an interesting dataset from the Chicago Police Department about violence. So please come by our poster for more details about that. To conclude, I think a key takeaway message is if you don't a priori know what kind of biases your model or data has, then using a transparent model to try to analyze the model or the data could help you reveal some interesting biases to further look at. Thank you.
Hi, I'm here to present an opinion piece, and the paper has no visualizations, and so while I made a couple of slides, an obligatory way, I think it's better that the talk actually have no slides, so I'll just read off some notes. I think a lot of us are used to hearing things like, I work with doctors. They're interested in predicting diagnoses, mortality, recognizing cancer in images. We can train a model and it might perform well, it might give accurate answers, but I can't tell a doctor the neural network tells me the patient has cancer. They won't accept that. They want an explanation. They want interpretable models. That sounds great, but the problem is interpretability is a common word and not a technical word. And so the problem is that by itself doesn't give a sufficient foundation for a field of study. If we want to build things that actually address the concerns of doctors, we need to avoid making sweeping claims, and we need to drill down and figure out what exactly are the desiderata that we are, in the business of providing. In other areas of machine learning, this is a little bit better established. There's a clear API between the model builder and the stakeholder, like say in image recognition. But interpretability, even if you get, I'm looking at Rich here, and we've had some of these conversations, but if you get even 2, I think, machine learning scientists who thought about this problem in the same room, they will not share the same notion of what this word means. So there's a serious hash collision problem. The word addresses a lot of different desiderata, like does this model actually capture the difference that makes a difference? A real causal understanding of the dynamics of the environment? Does it just give us some tuition as modelers that helps us to build better models? Does it give us some comfort that, like, I like this model, it's my friend, I feel like it, picks up on the same correlations as I do. And now you have a whole basket of solutions that are thrown at the problem, because that's ultimately what our reward signal is as modelers. We're here to present solutions, and we get papers accepted when we present algorithms, not for creating works of critical writing. So, in the rush to implement and publish algorithms, I think some important questions are overlooked. We're trying to build the platform before we build the service. So I think we should be asking, so I moderated the interpretability discussion section at Ian Goodfellow's slumber party in Mountain View recently, the self-organizing conference. And my one directive was, just don't say any sweeping claim about interpretability. Say, who are you building this for? Or who is the stakeholder? What do they want and what are you building? So we were forgetting to ask, who is the stakeholder? What do they want? Does this address an actually addressable concern within the current machine learning paradigm, or is this asking for something that you can't get out of your model. Like a linear model, no matter how simple, is not telling you causality. Are we looking at cases where people have real problems, or are we trying to placate people? So I think we need to ask these questions seriously. I mean, these are hard questions, and it's just as easy to be dismissive as it is, it's just as wrong to be dismissive as it is to sort of make a blanket statement, because this refers to a whole lot of concepts, but I think we need to take the problem formulation more seriously. So I also don't have a poster, but I will stand, over at the end on the right, and I'd be happy to have this debate with anyone. All right, thank you.
Hi, my name is Maruan, and I'll tell you about some interesting properties of model explanations. This is a joint work with Avinava, Dubey, and Xing. So there are different ways to define an explanation. We follow the line of work where we define explanations as linear models that approximate the decision boundary of a more complex model in a local neighborhood. Features used by explanations and by the predictive model itself may be different and often are selected to be different for interpretability purposes. So we'll look at two ways of constructing explanations. The first one is post hoc explanations, which are constructed after the model is trained. And the second one, when the explanations are generated on the fly. So the model learns to generate explanations and then to provide predictions along with explanations. So in this setup, we'll ask three questions. First, are the explanations consistent under certain conditions? Next, if the explanations are generated along with predictions, does and how that affects the performance of the model? And finally, what can we say about the data patterns that the model picks up by looking and visualizing explanations? So to answer the first question about consistency, we use the setup where we have a predictive model and we have different sets of features. One set of features for the model, one set of features for explanations denoted C and X respectively. We corrupt the features that are used by explanations with some noise. In this case, for example, we select a subset of features only and require the explanations to fit the subset of features to approximate the prediction. And then we'll look whether they are consistent. So we see that the blue curve shows us that no matter how small the set of selected features used for the explanation faithfully approximates the decision boundary of the predictive model. Or in other words, explanation overfits. If we look at the jointly learned explanations with predictions, they are consistent because the performance deteriorates with the less and less informative subset of features. Now, when explanations are generated along with predictions, how does that affect performance? Does it mean that the performance necessarily goes down? It turns out that when we have enough data, the performance of a deep network that produces explanations matches the performance of its vanilla counterpart. When the data is scarce, on the other hand, learning to explain regularizes the model and is able to even improve performance. Finally, having access to explanations allows us to visualize different patterns that the model picks up from the data and correlate them with different features. So for more details, please stop by our poster. Thank you.
As old as I am, I don't think I've ever given such a short talk in front of such a large audience. Wow. I'm going to give you two pieces of context and then tell you a little bit about what's replicated in a poster. First one comes from a paper and a picture you're all familiar with. I'm from Canada. In Canada, nobody would say this dog is standing. That's not what dogs do, right? So the motivation for the investigations I'm doing with a PhD student of mine are to understand deep learning well enough to be able to factor what's learned and do the equivalent of what we used to do in our old algorithmic programming languages, that is, insert print statements so we know what went wrong. So you think about it that way. Another way to think about it is that for those of you who are old enough to remember John McCarthy, his program, The Advice Taker, was pretty simple. Is if the advice taker produces an inference from what it knows, and it says this dog is standing on a hardwood floor, it's obviously hiding, probably ate the cat. You should be able to tell the system that this dog is not standing, not by producing 30 million new images. So just keep that in mind. So the following is just an exercise in trying to factor deep networks and to be able to visualize where things go wrong. We call that deep visual explanation for obvious reasons. Consider the experiment where you have this design of a system that looks at a long sequence of images. It's training. You can typically use your favorite neural network. We're looking at convolutional neural networks only because they're complicated enough to give us some factoring information. And what you want to do is instrument the network so that when performance accuracy goes down, you know where to look to try to get an explanation of why that performance goes down. In this case, it's pretty simple. The dogs in these pictures, when the system encounters that, tries to classify them, the performance should go down because dogs don't have pointy ears. We're not there yet, and the future work is about doing language analysis. So the only reason for picking this particular heuristic, in our case, Quebec-Leibler divergence, is just to measure a differentiation in ground truth versus what's learned in a distribution, to be able to focus where to factor the network, to look for some kind of visualization in terms of a heat map or something for humans of a subspace of the large dimensionality. This is just an attempt to explain, no pun intended, explain how to use that calculation to build an image map, a heat map. I can explain it in more detail later. What you get is what you see in the middle is a heat map. You multiply it by the original image, and the explanation, in this case for ease of representation converted to gray levels, is just to say, here is, in this case it's a BGG network from the Oxford group, say this is why this was a picture classified as a dog and not a cat. And that's it. Thank you.
Hi, I'm Lisa Ann Hendricks, and I'm presenting work Rounding Visual Explanations, which is done with Rongheng Q, Interpretable at UC Berkeley, and Zana Bakata at the University of Amsterdam. Okay, so what is the problem we're interested here? So clearly it's explanations, but what kind of explanations? We want to produce textual explanations. So let's say you have an image, like the one on the left, of a cardinal, and you have a deep net which can reliably classify this image as a cardinal. We want to build a model that can output a textual explanation that says why the label cardinal makes sense for this image. So in this case, an explanation like, this is a cardinal because this is a red bird with a black cheek patch and a red beak would be a good explanation. So two things to note about this explanation. One, the explanation is image relevant. It's talking about things that are in the image. This is a red bird. And it's also talking about discriminative features. So a black cheek patch is not something you see on all red birds, and that's its discriminative for cardinals. All right, so this is from previous work that was presented at ECCV 2016, and one question we asked ourselves is, are all of the textual explanations that we produce, are they all image relevant? And it turns out that what we see is a lot of explanations like the one on the left, like this is a rufous hummingbird because this is a green bird with a red throat and a long black beak. Clearly this is a bad explanation because this bird is not green and it does not have a red throat. So what's going on? Basically what's happening is the model knows that green bird and red throat is a discriminative property of rufous hummingbirds because many rufous hummingbirds, specifically male rufous hummingbirds, have these attributes. So the model learns to talk about discriminative things without necessarily grounding it in the visual evidence. And this is clearly bad for explanation systems where you want to build trust with the human user. So the model that we're presenting here not only talks about discriminative features, but then goes and grounds explanatory evidence in the image to ensure that the explanations are image relevant. So our model produces explanations like, this is a rufous hummingbird because this is a small brown bird with a white breast and a long black beak. All right, so quick overview of how we do this. The way we do this is we generate many different explanations, and then we use a grounder to ground explanatory evidence in the image. And then we have a phrase critic that we train to ensure that sentences that are image relevant have higher phrase critic scores than explanations which are not image relevant. In practice, does this work? We have a human evaluation where we ask people to look at our explanations and mark how many noun phrases are correct. And we find that our model does better than baselines and other simpler methods that we propose. Finally, qualitatively, we can understand why we see the quantitative results. So at the top, I have an example of a golden-winged warbler. So the previous method, 1, mentions that this bird has a black crown, which isn't image relevant. Our model talks about discriminative information, and all the discriminative information that it mentions is actually image relevant. So hopefully this kind of explanation would be better for building trust with human users. If you have any more questions, please feel free to come by and talk to me at my poster in the back. Thank you.
Hello, Sapna Agarwal. I'm going to talk about a probability series expansion classifier that is interpretable by design. So the basic question is I want a fast adaptable classifier. So I want to estimate the probability of some outcome given a number of features. And I'd like to build this up from individual probabilities of the probability of the outcome given individual features, or given a combination of features. So the question is, how do we combine these individual probabilities into an overall estimate? Because that way we can then understand exactly what probability contributed to the overall estimate. So now the challenge is that there's not really a good first principles method for combining these probabilities when they can potentially be dependent and have all sorts of correlations. So the simplest thing you can think of doing is, well, let's just average all the probability estimates. So the probability of the outcome given an individual feature, just average over all of them and say that's our overall estimate. Now if we can refine that a bit more by saying let's make it a weighted average and weight for different effects that we want to account for. Say if a probability is exactly 0 or 1, we're going to want to weight it higher, because then it doesn't matter what other features are. We know that it's 0 because it has this feature. And now if a probability has less supporting data, we want to weight it more as well, or weight it less. And additionally, if a probability gives new information, perhaps we want to give it more weight. And so adding all this together, we basically build a hierarchical weighted average. So if we build a model like that, we can actually get pretty good results. So here are on some sample data sets, we're matching the accuracies that you get out of the random forest model. But so now it's promising, we're getting good accuracy, but we cannot use it to explain why we're getting a given result. So for instance, on this data set of congressional voting records, we can look at one example which we misclassified. You can see that certain combinations of features indicate that this representative should be a Republican, while certain other groups of features indicate that this representative should be a Democrat. So you have contradictory information, but now what you can see is how much that certain pieces of information were weighted more, and if you look at it by feature, what you see is that there's a higher probability or higher certainty for the Republican features, and that's why the model weighted it higher. And so, come back to the poster, I'll show you the details of the model, and you can see how this works. And the basic idea is just sort of taking a bunch of feature probabilities and combining them in a tree. So thank you.
Good afternoon. I'm going to talk about globally optimal symbolic regression. My name is Baruch Shiver. I'm from IBM Research AI, and I'm not going to name all my co-authors because I have only 3 minutes. I'm sorry. So what is symbolic regression? Symbolic regression is basically a way when you have some observable, let's say we have x1 observed x1 to xn and we have a y, we would like to find a closed formula or a closed mathematical expression that would represent y as a function of the xi's. And you can imagine that sometimes it's it's clearly explainable, and sometimes it's desired to find such a closed formula, especially when we are looking at a physical or a chemical phenomena that we would like to explain. And people looked at it. There is a lot of prior work in this area, but most of the methods that were proposed were based on heuristics, mainly genetic algorithms and derivative of genetic algorithms. So what we proposing is basically to look at this problem of finding the mathematical expression as an optimization problem. we show a formulation that basically takes this problem and formulates it as a non-convex mixed integer programming problem. And then we solve this problem, and by doing it like this, not only that we get an expression, we can show that this expression is the optimal expression under the objectives that we used. And the objectives that we used is to find the simplest expression. And to find the simplest, you can define simple in many, many ways. We used one way, but if you think about another way, we can formulate the objective in a different way and still find the globally optimal such expression. And to demonstrate that this really has some, there is some utility in what we propose, we looked at two problems. So we used NASA data and we reproved Kepler's law. And it took us less than him to do it, by the way. And the other one, we basically built the pendulum and we took video picture of the pendulum, and using this we were able to rediscover Galileo's pendulum periodicity equation. So we are looking, of course, for other applications, better, a little newer, if possible. So how do we do it? What we are basically doing is we are representing the expression. Probably all of you know that you can represent an expression by an expression tree. So expression tree is exactly what it sounds. We have nodes, we have edges. Each node is a constant, a variable, or an operator. And the links define the relations between these operators or operations. And then what we are doing, we are formulating a problem, which is, as I mentioned, a non-convex integer problem, where we want to minimize the complexity of the expression under several constraints. So the constraint basically makes sure that it's a tree, and they make sure also that the error is bounded. And if you go to the poster, I'll show you more details about the results that we got for Kepler's law and for Galileo pendulum equation. Thank you.
Hi everyone, my name is Avinava. Disclaimer, I'm not a computer scientist. I do philosophy and art history. So my paper is to offer not so much a solution of interpretability, but maybe a contribution to a critical vocabulary that addresses all the shortcomings of the notion of interpretability. Usually my research is in the implications of machine-generated imagery for art and art history. Why is this relevant? Because I think with the emergence of interpretable machine learning, art, history, and computer science suddenly both struggle with the same kind of questions. And one of them is, what is the epistemic value of intuitively interpretable images? The notion of I know it when I see it, which is the title of my talk, indicates that intuition depends on visualization. Visualization, in turn, enables but also impedes intuitive interpretability, as it implies at least two, we could call them hidden layers of pre-interpretation, dimensionality reduction and regularization, and you're probably familiar with both of them. Internal states of machine learning models are spatially non-intuitive in two different ways. They encode multiple distinguishable properties of reality at the same time, distributed over a large high-dimensional space. As such, internal states of machine learning models are non-concepts, that's what I would propose, that can only be represented in terms of what they are not, which, by the way, mirrors long-standing discussions in the humanities on meaning and interpretation. This deficiency of intuition in the face of the non-conceptual becomes particularly problematic when intuitive interpretability informs the training of machine learning models as well. And as an art person, I have to show at least one piece of art, or so-called art. This is Gabriel Go's image synthesis from Yahoo's open not-safe for work. You might know this one. Gabriel Go took Yahoo's open not-safe for work model that distinguishes workplace appropriate from so-called not-safe for work images. And this distinction is, of course, the origin of the notion of I know it when I see it. And he explored different activation maximizations. Here are the least pornographic images. So where do these kind of peculiar landscapes come from? Most likely they are the result of providing concrete negative examples to the model of your training. And we can specify the kind of examples used by generating more activation maximizations and letting the same network that analyze open not-safe work also classify them. But what is the negative of pornography? These images indicate that because there is no intuitive answer to this question other than everything that is not pornography, here the negative was approximated with a positive concept, perhaps even from a single ImageNet class. What we see is approximating non-concepts with positive concepts introduces a significant human aesthetic bias into the equation, which links intuitive interpretability directly to questions of fairness, transparency, and accountability. Hence, to make the notion of interpretability more rigorous, I would propose we have to first identify where it might still be impaired by intuitive considerations. So we have to consider it precisely in terms of what it is not. My poster is over there, and I would love to talk to you and answer your questions. Thank you.
Thank you to all the Spotlight talks. We're now going to have a coffee break where you can also look at the posters in the back. At 4:15, the coffee break comes to a close, and we'll have the presentation of a new interpretability and explanation challenge. So you should all come back at 4:15. Thank you so much.
Mentioning it, he'll be up next after that.
Hey, it seemed like you wanted